Welcome back. Our goal today is to find the area of triangles. In geometry, we learned that the area of a triangle could be found by taking 1/2 times the base times the height. In the case of a right triangle, the base was the length of one of the legs, and the height was the length of the other leg. In the case of an acute triangle, the base was the length of one of the sides, and the height was the length of the altitude drawn to that side. In the case of an obtuse triangle, the base was one of the sides, and the height was the length of the altitude taken to that side. Now we can use the same kind of logic we used to derive the law of sines to find a nice formula for the area of these triangles. If we label these capital A, capital B, and capital C, as we did before, and then across from those, lowercase a, lowercase b, and lowercase c for the side lengths, we can say that the area of this triangle, the acute one, is 1/2 times the base, which is the length c, times the height, which is the length h. And then, as we did for the law of sines, we took this right triangle and said sine of angle A is equal to opposite over hypotenuse. We then said we can solve for h by taking h is equal to b times sine of A. We will substitute this expression into here and say the area is 1/2 times c times b times sine of the angle A. Let's repeat that same exercise over here, where if I label this angle A, angle B, angle C, and across from them, lowercase a, lowercase b, lowercase c. The area is still 1/2 times the base, which is side length c, times the height. And we go in and look at this right triangle and say, well, we would like to know that angle, so we can say the sine of that angle equals opposite over hypotenuse. Remembering that this is angle A, that means this is going to be pi radians minus A. We can say that sine of pi radians minus angle A is equal to opposite over hypotenuse. But remembering the identity that sine of pi minus an angle is the same thing as sine of the angle itself. We can once again solve for h, so we can substitute. H is equal to, multiply the b across, b times sine of A, and take this expression and substitute it there, which means we have 1/2 c times b times sine of angle A. We have the same relationship twice. Now, just out of curiosity, let's try this one as well. If we take angle A, angle B, angle C, lowercase a, lowercase b, and lowercase c, we can say the area is 1/2 times c times b. In order to discuss the relationship between this and that, we remind ourselves that sine of 90 degrees, or pi over 2 radians, is simply equal to 1. So there would be no problem writing this as times sine of angle A, since this quantity is simply 1. Why would we do that? Just multiply by 1 here. It's so that we can establish the exact same expression for all three cases of these triangles. Because back in geometry, we learned that there are only three things an angle can be. It can either be right, acute, or obtuse. And we have shown that we can find the area of a triangle regardless of what size the angle A is using the same formula. That means this formula has to apply for any triangle with any angle for A. What we were just able to show was that given the right type of information, we can find the area of this triangle by 1/2 c times b times sine of angle A. And in many cases, we prefer alphabetical order because it's more aesthetically pleasing. And so if we notice the arrangement of this information, we have B, A, C as a side-angle side arrangement. So as long as we have side-angle side information, we can use that formula for any angle A, because we showed that this formula was appropriate whether A was acute, right, or obtuse. So that means we can look at any angle, no matter what the letter is, and do side angle side to find the area. So if we go from angle B's perspective, side angle side would be 1/2 lowercase a, lowercase c, times sine of capital B. And then from angle C's perspective, side angle side would be 1/2 lowercase a, lowercase b, sine of capital C. All three of these formulas will give you the same area of this triangle so long as you have side angle side information. Let's try an example. We are given the following information. Angle A is 60 degrees, lowercase b is equal to 7, lowercase c is equal to 11. And we would like to find the area of the triangle. So first, let's label the triangle and see what we have. We've got angle A is 60 degrees, side length B is 7, and side length C is 11. And we realize that we have side angle side. What we want to do is find the area by the relationship we were just able to find. 1/2 BC times sine of angle A. And we realize in this case we have all the necessary information, we just have to put the numbers in there. So this is 1/2 multiplied by side length B is 7, side length C is 11, and sine of the angle A is 60 degrees. Now we just have to plug that into the calculator, and we get 33.34 square units. We should put approximately, since this is a rounded quantity. In the case we just had, we were given information in the form side angle side, which fit our formula perfectly. But let's imagine that's not the case. What if we're given angle A is 53 degrees, angle B is 39 degrees, and side length C is 15. We would like to find the area of the triangle. If I try to draw this with angle A in the lower left corner and angle B in the lower right corner, angle C is up here, so the opposing side, C is down here. The information I've given is angle, side, angle, which is not side angle side. So when I draw the rest of the triangle, and I label this, I think to myself, I would like to find the area the way I did before, using side angle side. So that's lowercase b, lowercase c, times sine of angle A. I have side C, I have angle A, but I don't have side B. Now, of course, I remember that angle side angle is a case we solved using the law of sines. So I could say sine of angle A over lowercase a is equal to sine of angle B over lowercase b is equal to sine of angle C over lowercase c, and inspect. The piece that's missing, side B, is what I want here. I already have angle B. So if I can get either this ratio or that ratio, I'm in the clear. I have two angles. And if I have two angles, that means I have them all because they have to add up to 180 degrees. A plus B plus C is 180 degrees. And I'm missing capital C. So we'll say capital C is 180 degrees minus A minus B. Which will come out to be 88 degrees. Okay. Now we have all of the angles. We realize that we have an angle and the opposite side, which means we have this entire ratio, and we can leverage that to find what we want to find. So if I write that ratio down, sine of angle B over lowercase b is equal to sine of angle C over lowercase c. And I can fill in the numbers. Sine of angle B was given 39 degrees. Lowercase b is what I'm trying to find. Sine of angle C, well, we already found angle C to be 88 degrees. And the lowercase c was given in the problem to be 15. To solve for b, I will simply multiply b to the other side to get it in the numerator, and then multiply the reciprocal of this to the other side. So b is equal to sine of 39 degrees multiplied by 15 over sine of 88 degrees. When we plug this into a calculator, we get b is approximately 9.45. Now that we have this side length, we had the piece we were missing, we simply have to fill this out. 1/2 times 9.45. I should put approximately since we have a rounded quantity. C, which is given to be 15. And then sine of angle A, which was 53 degrees. And I can punch this into a calculator, and I get my area to be 60.08 square units. And there we have it. So even if we're not given side angle side at the beginning, if we can solve the triangle, we can always get the side angle side information we need. In the last problem I mentioned, we could find the area for the angle side angle case because it was not ambiguous. But what if we have information that leads to an ambiguous case? Let's say we're given angle A is 40 degrees, lowercase b is 10, and lowercase a is 7. We would like to find the area, perhaps. If we try to draw this, I'll put angle A in the lower left, and since we can choose how to label the angles, I'm going to put angle B down here. So the opposite of angle B is going to give side length B is 10. And then opposite of angle A, we're going to put side length A. And we realize we have angle side side, so this is going to give rise to the ambiguous case. If I put side A to be that way, then I have one case of the triangle, but we already know from last time that we can also close a triangle this way and have a potential A equals 7 here. Now in the two cases, we mentioned that there was a C1 for this entire thing, but there was also a shorter C2 for the smaller case of the triangle. Now if we were trying to find the area of this triangle using the given information, we would go side angle side and say that the area is 1/2 lowercase b lowercase c times sine of the angle A. Now, we were given two of those pieces, and we need to find lowercase c in order to find the area. However, when we did the ambiguous case, we found that there were two different values for c, meaning two different values for the area. So in the ambiguous case, we are not able to find a unique area, but we can find two different areas. And that's it for finding the area using the side angle side method. I'll see you guys next time for the law of cosines.